All right. In this lecture, we are going to take what we've just learned with bonding, where we're typically talking about two species coming together, and we're going to look at what happens now when we combine that into a solid of more than just two things. And so we're going to start by looking at crystallinity and amorphous behavior. All right. And so we kind of start with a hypothetical question here is there an ideal way to store equal sized spheres? And what I'm going to kind of show you to make you think about this is kind of two scenarios with equal sized spheres. So if you are all aware of ball pits, right? This is a ball pit. Each one of the balls is an equal size sphere as every other, and it's in a confined space, right? You probably haven't gone to one of these in a while, both because of COVID and that you're not five. But that is one way, right? If you look at the balls in there, think about how those are stored. And the other way is think about this. So this is a sketch I found, basically a historical sketch where they used to store cannonballs, right? So if you've got a lot of cannonballs, you want to put them somewhere, and so they kind of stack them in this way. And again, we're going to assume that they're all the same size. So I want you to think about those as an example. And the first, the question I have here for you for your quiz is take those two examples and how would you describe the arrangement of these balls in the ball pit and the cannonballs in the pile? So answer that. And then your guess here, or maybe you know a little bit more, is which one is more efficient. And so when I'm talking about efficient, I'm talking about packing. So think about what that means as well. So go to the quiz, answer that, and come back, and we will discuss. All right, so let's go ahead and take a look at this. So hopefully you were able to sort of describe these two scenarios, and based on your answers, the two things I'm going to guess that you came up with is when you looked at the ball pit, you kind of think of this as chaotic, right, or disordered, just random. These balls are just kind of everywhere, right? Whereas if you want to kind of describe these cannonballs, they're very ordered, right? They're very uniform, and so forth, right? So those are kind of, you've got kind of chaotic versus very ordered and uniform. And so, as you might guess, a more ordered structure is typically going to be the more efficient. And when I'm talking about efficiency here, I'm referring to the use of space, right? So more, less empty space between the balls. So here we would guess that the empty space between these balls is less than kind of here in the disordered or chaotic structure. And that's going to be the case in materials, in solids. And so I'm going to take you through the two examples and kind of think of the ball pit and think of the cannonballs as we go through this. So ordered packing of these spheres tends to result in shorter bond distances, right? So things are closer on that bond energy diagram, and so they get closer to energy well, right? So that's what happens with ordered structures. Sorry, this is the loose one here, so it's further away. So if we kind of compare the two, so loose, right? There's loose random. There tends to be greater distance between two spheres, and therefore it's at a higher separation distance r, and so it's more to the right. And then a dense ordered, the balls are closer together, and so that bond distance is shorter, and so it's in that energy well. So that kind of relates back to what we talked about in bonding. So this is ball pit, this is the cannonball piles. And so ordered structures tend to have lower energies because, again, the bond is at the minimum energy value that we see. All right. So let's look at these and kind of compare them to real materials now. So if a material doesn't have that ordered structure, these are called non-crystalline because a crystal is an ordered structure. So it's non-crystalline. You can also refer to it as amorphous. That's a very common term for this. And then the more common term that you've probably heard before is a glass or glasses. So this ball pit is amorphous because it doesn't have any sort of ordered structure to it. It's very loose, chaotic, and unorganized. So this happens quite a bit, like I said, in glasses. So what we call glass is actually more correctly an inorganic glass because it is predominantly SiO2. And it doesn't have an ordered structure. So you see here that we have silicon and oxygen, and they're bonded together, but the way in which they're bonded is very chaotic and not ordered in any way, right? It's a very kind of random network that we see here. So this is non-crystalline, and so this is typically the foundation of what we call glass. But also, the reason we call this inorganic glass is because many polymers or plastics tend to be amorphous or maybe only partially crystalline. So this kind of structure is very common in polymers. All right, so let's kind of understand how it happens. So amorphous materials can happen in a number of different ways. One of them is that we can rapidly cool a liquid. So a liquid, as we know, has that same kind of chaotic, disordered structure. And so if we cool it down really quick, then it can kind of freeze in that structure, that non-ordered structure. So we kind of lock in that structure. So this is how those inorganic classes and some polymers become amorphous, is that they're cooled down very quickly. The other way in which it can happen is kind of inherent to the material itself. SiO2 and the structures, the crystal structures, which we'll get into later in this chapter, but the crystalline structures of SiO2 are fairly complex. They have a complex regular structure. Same thing with polymers. Polymers has very complex arrangements, and so those complex arrangements kind of prevent the ordering to this structure, so it becomes more and more difficult. So that's what happens with polymers as well. Polymers are very large molecules, very complex crystal structures, and so by having that complexity, it kind of prevents that crystallinity from happening, and so you're more likely to get this kind of disordered stuff over here. All right, so now let's look at the opposite. Let's look at what we call crystalline materials. So they have a structure to them, an order to them. And so the term we like to use is periodic. They have a periodic arrangement. And so that's the cannonballs, right? They have a very ordered structure to them. Also, since I talked about glass, SiO2 can crystallize, and one of the crystallized forms is what we call a quartz. So you might be familiar with quartz. So it's a natural crystal, but it can also be used in other ways as well. Also, most ceramics, like quartz is a ceramic, porcelain, that's a ceramic, and really any ceramic you can think about, those tend to be crystalline. And also metals. Almost all metals are crystalline. There is a whole field of amorphous metals, but those are only formed in very, very complex kind of lab settings, because if we go back, they require this rapid cooling. So if we want to make amorphous metals, or sometimes they're called liquid metals, we basically have to rapidly cool them. Or we can kind of try to make a really complex structure with metals. And so that's another approach to doing this non-crystalline. But again, for the most part, metals and ceramics are crystalline. So that kind of takes you through the basics of what we're going to talk about in this chapter, and that is the structure. So we've talked about atoms themselves, molecules. We've talked about the bonding between atoms and molecules, and now we're going to see how those atoms, molecules, and bonds are put together to get a solid material like quartz or like a glass or a metal or a polymer, how those crystals are put together.